Hey there. So, in the last video, we went ahead and talked about a couple of ideas that are important uh, for momentum. Of course, first we define momentum as an object's mass times its velocity, and we're going to clarify that point a little bit more explicitly in this video by the end of it. Um, because really in the last video, what we wanted to build up to was grouping little point particles into systems of particles. Point particles are extremely useful since we know that the time derivative of their mass is zero. That's by definition of them being point particles. Uh, and then after that, we just practiced grouping together point particles in systems. Everything around the system was its environment. And then depending on how you define your system and your environment, that changes the internal and external forces that are exerted on the components of your system. All right, so next we're going to try to build up to the conservation of momentum, and I'm going to do this just by bringing back my system of three particles that I used from the last video. So this was just three particles. We labeled their interaction forces as such. These were generalized forces, although we could think of them as the gravitational pull between these particles. Um, in blue here, we're defining our system to be all three particles, so our environment is essentially nothing around them. All right, now let's go ahead and throw in some axes, x and y axes, so we can define our space. And after this, we're going to throw in some vectors, some position vectors that point to each of these particles. All right. And the first thing that I want to talk about, right, because in the last video, I really just referred to velocity and acceleration, but let's go ahead and make sure that we're very clear on what those mean. So each of these particles have some position in space that from this origin we can label as vectors. So R1, R2, R3, or Rn for whatever particle n that you're talking about. When we take the time derivative of my position, that is the definition of velocity. So for these particles, r dot n is equal to Vn, and when I take the second derivative with respect to time, that gives me the acceleration of one of those particles. So I just want to be very clear that I can use r dot n or Vn interchangeably when I'm talking about the velocities or the accelerations of the particles. Let's just be very clear on that notation. Okay, so from here, I want to give an example relating all of this notation together, right? Uh, because this is a lot of different ways of kind of saying the same thing, but acknowledging all of them is pretty important. So, for example, if we look at this particle up here, m1, we could say that the rate of change of particle one's momentum with respect to time, that is the definition of the total force acting on one. What are the forces acting on one? Well, we have these little two forces, F2 comma 1 and F3 comma 1. Those forces result in an acceleration of particle 1, right? F equals ma. And then I simply substituted in my definition that the acceleration of particle 1 is uh, the second derivative with respect to time of r1. Okay? So these are five separate ways of kind of saying the same thing. And it's important to be able to use them interchangeably. All right. So, and remember, for this system, we talked about this in the last episode, we determined that all of the forces in this system were internal. So that's the key assumption going into this whole thing, is that our forces are internal. All right, I'm going to go ahead and pull that image back up. There we go. Okay. And we're going to start creating equations of motion for each of these masses now. This is not too challenging. So we know that here, actually we'll go like this. All of these definitions are equal, right? So I'm going to choose two very useful ones, this guy right here and this guy right here. And we're going to set up an equation relating each of these for each of these particles. So for M1, we have that the sum of the forces F2, comma 1 and F3, comma 1 equal M1 times its acceleration, R1 double dot. All right, very simple. Same thing for R2. Take the forces F1, comma 2, F3, comma 2, add them together, and those equal M2, R2 double dot. We can do the exact same thing for M3 as well. So these are just equations of motion for each of these point particles. Now, we have to bring in Newton's third law. Remember, every action force has an equal and opposite reaction force. So let's go ahead and look at this interaction between M1 and M3, right? M1 is pulling M3, which gives us F1, comma 3. Likewise, M3 is pulling on M1 with the exact same magnitude force, but it's in the opposite direction, right? So F3, comma 1 equals negative F1, comma 3. That's Newton's third law. We can apply this to our other forces as well. F2, comma 1 and F1, comma 2 are equal and opposite, and F2, comma 3 and F3, comma 2 are equal and opposite. All right, so we pointed out Newton's second law. Or not second law, third law. So now let's say that we wanted to take these three equations of motion and add them together. Then what we would see is that all of our forces would cancel out and equal 0. I went ahead and labeled, we can see correspondingly to the colors here. F1, comma 3 cancels out with F3, comma 1. F2, comma 1 cancels out with F1, comma 2. And F2, comma 3 cancels out with F3, comma 2. So these forces sum to 0. And of course, on the right side of our equation, we add up these three guys together. And there we go. All right. So I'll just go ahead and write our statement very nice and cleanly. Now, what's important here? We determined that, the sum of all of our forces are equal. And so, somehow the accelerations of each of the particles are going to add together in this way that they equal 0. But we can't conclude anything about the acceleration of each of these particles, right? M1 could be accelerating some random way, M2 could be, and M3 could be, right? We're not saying that the accelerations of each of the particles in this system are 0, okay? So we might not immediately go like, oh, this is a mind-blowing conclusion or anything. But we can manipulate this and turn it into a very useful one. So the first thing we're going to do is, this might seem awkward at first, but I'm just dividing both sides of my equation by m1 plus m2 plus m3. Of course, the left-hand side is going to stay 0. Right? And again, I'm kind of asking the same question again. Is this a useful statement? It's only useful if we interpret it in a specific way. And the way that we're going to interpret this, first we're going to have to add in a new definition, and it's called the center of mass. The center of mass is generically defined as the summation of mi times ri, for all of your particles, and then divided by summing up all the masses of your particles. I don't really like just reading out summation definitions, so let's go ahead and jump right in to what that would look like for this example. So for our example with the three particles, it would be m1 times r1 plus m2 times r2 plus m3 times r3, all divided by m1 plus m2 plus m3. All right, let's go ahead and see what this looks like. Because what we're doing here is we're inputting 3 vectors and we're outputting a single vector, which really kind of looks like some type of average of our positions, right? We're scaling each of these up based on the masses of the particles that the positions are associated with, and then we're dividing the whole thing out by the total mass of the system, right? So that's going to give us something, some kind of average. And I don't know exactly what that location is for these 3 particles, but it's going to be somewhere, right? I went ahead and labeled it kind of in the middle of all 3. Of course, if like M1 was super huge, the center of mass could be skewed more towards M1. All right, so that's the definition of center of mass. We have taken the vectors that point to all of our particles and kind of reduced it down into this really nice, elegant single vector that represents the position of our object in a sense, or uh, or our system. So again, our center of mass represents the position of my center of mass. Keep in mind, we can take time derivatives of this guy. So the first derivative with respect to time is the velocity of my center of mass. And the second derivative with respect to time is the acceleration of my center of mass. So let's go ahead and compute what that second time derivative would be. All I'm doing here is I want to take the second time derivative of my center of mass. That involves me plugging this guy in right there, right? And taking its second time derivative, keeping in mind that each of my point masses have a constant mass because, again, by definition. Then we go and get this statement right here. This is the acceleration of my center of mass. All right, now watch this. Notice how this guy here is the exact thing that I said up here was 0. Aha, so now you can kind of see why I divided awkwardly by m1 plus m2 plus m3. Because what we can end up saying is that the acceleration, r double dot of my center of mass, the acceleration of my center of mass is 0. And what was the assumption to this whole problem? I only had internal forces within my system. Another way that we could say this statement is if I have purely internal forces in my system, is that I have no external forces acting on my system. So those are 2 equivalent statements. All right. Our next task is to make this look like some statement of force. And remember that a force is the time derivative of momentum. The first thing that we're going to do, we can think of force like F equals ma kind of. So maybe it would be intuitive to multiply uh, our center of mass by m1 plus m2 plus m3, the total mass of the system, and we do the same deal with the right side of our equation. Remember, m1 plus m2 plus m3, that's the entire mass of the system. I'm just going to label that capital M. And notice how kind of the two modifications that I've done here cancel each other out. At one point I divided by m1 plus m2 plus m3. Now I'm multiplying by m1 plus m2 plus m3. All right, so we've got this statement here. Let's go ahead and pause for a second and recall exactly what this definition means. When I have only internal forces in my system, then this here is the total mass of my system. This guy here is the acceleration of my system's center of mass. multiply those two guys together, it equals 0. All right, perfect. We're still not there yet. Let's go ahead and remember that our momentum, by definition, here, let's go ahead and add that triple bars, is defined as mass times velocity, and that then you could take the time derivative of it. And in a perfectly general situation, we apply the product rule and get the following. I'm going to introduce a new definition that really should make a lot of sense, that the momentum of a system is defined as the total mass of that system times the first derivative of my center of mass with respect to time. Now, does this make sense? Let's go ahead and start with that. So for my system of 3 particles, the m would just be m1 plus m2 plus m3, and r dot, center of mass, would be m1 times r1 dot plus m2 times r2 dot plus m3 times r3 dot, all divided by m1 plus m2 plus m3. These guys would cancel out with each other, and remember, r1 dot is just another way of saying, v1, and r2 dot, v2, r3 dot, v3. So really, each of these guys then would just each be a momentum of an individual particle. And so we see that this definition of the momentum of the entire system is really saying that we just take the momentum of particle 1 plus the momentum of particle 2 plus the momentum of particle 3, and we add them together. So this definition makes perfect sense. Let's go ahead and also note, let's recall from the last video when I talked about the momentum of a ping pong ball. A ping pong ball was not a single particle there, right? A ping pong ball is made up of lots of little itty bitty point particles, right? So I'm just going to read this statement out real quick. The ping pong ball object was a specific system of particles which happened to be useful to group together and call a single object. So really, we were cleverly defining a, quote, ping pong ball as a very specific system of particles. When we talked about the momentum of that ping pong ball, right, what we were really saying is that the center of mass of the ping pong ball was moving at 5 meters per second, and so, r dot, center of mass, this guy here was 5 meters per second. The mass of our ball is really summing up from I equals 1 to n, the number of particles that make up the ping pong ball. We're just summing together all of the little individual masses from each point particle. Okay? So with this definition in mind, we can go ahead and take the time derivative of the momentum of my system, and generically we get this statement here. Again, we're just applying the product rule. Now, both of these terms are going to go to 0. The first term goes to 0 because we already proved that it goes to 0 with this statement right here. The second term also goes to 0. Why does the time derivative of my mass equal 0? This is because I chose a specific group of point particles to make my system. My particles aren't just going to magically leave the system. Once my system's defined, everything that's in that system stays in that system. And then likewise, once I have a defined system, particles that are part of the environment, they can't just magically enter the system. This is a really hard, clear-cut definition, right? And so therefore, the mass of my system does not change with time. And so, we just identified that P dot of our system is equal to 0. That's exactly what my goal, that's exactly what my goal here was. Because the time derivative of my system's momentum is 0, this means that between any two events, the initial momentum of my system must equal the final momentum of my system, right? So these are two equivalent statements. We call this law the conservation of linear momentum. Remember, our only assumption for this entire thing, and of course, technically the number of particles, we only put 3 particles in there, but you could repeat this process for an n number of particles very easily. But the only other assumption was that all of our forces were internal. They were only between pieces or point particles that we defined within the system, right? So when we have that case, we can determine that the momentum of our system is conserved. And so that is how we get to the conservation of linear momentum. Really, this is just a byproduct of Newton's third law with some fancy rewriting. Okay? In the next video, I'm going to talk about how we deal with, well, the situation where there's external forces, right? Where not all of my forces are internal inside the system. But yeah, there's a lot of really important skills at play here. You got to be clever when you define your systems, and you have to be very clear with your definitions of things like the momentum of your system, like the center of mass. So yeah, with that, I hope you enjoyed that little video, and thank you so much for watching.